Welcome to the lecture number 16 of the course Quantum Mechanics and Molecular Spectroscopy. We'll just look at the final equation that we derived in the previous lecture and proceed with that. Toward the end of the last lecture, we showed that the probability of transition to a final state F is given by 4 pi square E naught square by h bar square E naught bar h omega Fi by omega square del omega Fi plus omega plus del omega Fi minus omega square F epsilon dot mu dot I whole square. Okay. I made a small mistake in the last lecture, is that this 4 does not exist, because when you write cos omega t you have 1 over 2. So that when comes out of this square or absolute square, it will cancel the score. So there is a small mistake, but that is not going to change the way we look at the entire problem. So P of t is just given by pi square E naught square by h bar square into omega Fi by omega square del omega Fi plus omega del omega Fi omega square modulus of half epsilon mu I whole square. Okay. Now there is one more thing, is when you are squaring this, so omega Fi square of course is equal to omega If square. Okay. So the transition, whether it is going from the state F to state I or state I to state F, this will remain the same. Okay. Now the other thing that we said, that when you have del omega Fi plus omega, this will correspond to stimulated emission, and del omega Fi minus omega, this will correspond to absorption. Okay. And we said this cannot happen simultaneously, either stimulated emission will happen or absorption will happen. Okay. So only one of the process can happen at a given point of time, and both cannot happen simultaneously. So if we consider for absorption, process from initial state I to a final state F, then Pf of t is given by pi square E naught square by h bar square omega Fi by omega square omega Fi minus omega square F epsilon dot mu I whole square. Oh, that is the transition probability for absorption process going from an initial state I to a final state F. Okay. Now one can also write very simply slight rearrangement. So P F of t, now we know h bar is nothing but h by 2 pi. Okay. So when we had pi square by h bar square, so h bar square is equal to h square by 4 pi square, or 1 over h square is equal to 4 pi square by h bar square. Okay. So one can think of this as, if I take this 4, so 1 over 4 h bar square is equal to pi square by h bar square. So I can always write this. So your P f of t can also be written as E naught square omega fi by omega square del omega fi minus omega square f epsilon dot mu I whole square. So P of this can also be written as E naught square by 4h square omega fi by omega whole square del omega fi minus omega whole square f epsilon dot mu I whole square. Now you can see, you can write in two different ways. Essentially the functional form still remains the same. So it will have the square of the transition moment integral and then we will have this delta function and some constants. Okay. Now the problem here is this, that how this equation, okay, will behave. Okay, that is what we want to look at. Let us look at the delta function, delta of some function x. Okay, this can be written as limits n tends to infinity 1 over 2 pi sine nx by 2 divided by x by 2. This is a way one can write a delta function as well. Okay. Now one can also write delta omega fi minus omega as delta omega. If one writes that, then your of delta omega can be written as, okay, limit n tends to infinity 1 over 2 pi sine of, okay, delta omega to n by 2 divided by delta omega by 2. Okay. Now, but what is your n here? N is just the time. Okay. So I can still rewrite as delta omega is equal to limit t tends to infinity is equal to 1 over 2 pi sine of delta omega t by 2 by delta omega 2. Now why I am using limit t tends to infinity? Because you can, we have all, but this is a valid limit, because remember when we drew this perturbation curve from 0 to t prime and goes to infinity. So time can go up to infinity without any consequence, because after t prime it doesn't, the perturbation doesn't exist. So one can think of this limit to be taken over. So this is same as extending our integral. So which means I can rewrite p of t of f, this is equal to pi square e naught square by h bar square, okay, omega fi by omega square. I had del of omega fi minus omega square integral f epsilon dot mu I whole square. Now this I will write in terms of the limit. Okay. So this will come out to be, there was a 2 pi, 1 or 2 pi, so that I can bring it outside. So pi square E naught square by h bar square omega Fi by omega whole square into 1 over 4 pi square, because and this pi square and this pi square will get cancelled, and this one will be sine of delta omega t by 2 divided by delta omega by 2 whole square f epsilon mu I whole square. Okay, where delta omega is nothing but omega Fi minus omega. Okay. Now, so I am going to slightly rewrite this equation. So Pf of t is equal to E naught square by 4 h bar square omega Fi by omega square modulus of sine del omega t by 2 by del omega by 2 square f whole square. So this is the probability. So now you can see the probability of a transition or an absorption from initial state to final state will depend on this transition moment integral and will get modulated by this function. So this is nothing but TMI, transition moment integral, and this is nothing but your modulating function. I'll come back to what modulation function really means, but just for a minute let's keep it, let's look at it. So I'm going to tell. Now what does it really mean? It means that your probability of function f of t equals to, okay. Now as I told you, this will depend on E naught square by 4 h bar square omega Fi by omega square sine square del omega t by 2 divided by del omega by 2, because the square, so I have just brought it out of square, and multiplied by modulus of f epsilon dot mu I square. Now this I told you is a transition moment integral, it is a definite integral. I will just write it as t and I take a square of it, so it will be t square. So your Pf of t is equal to E naught square by 4 h bar square omega Fi by omega square sine del omega t by 2 square of that and del omega by 2 square of that to t square. Now you can see for a given omega, okay, omega Fi is fixed because the energy difference between the two states is fixed. So your initial state and the final states are fixed, so omega Fi is a constant. Omega will vary because if your electromagnetic radiation varies, that will vary, okay, because you can tune the radiation, you can go from some frequency to some other frequency or some wavelength to some other wavelength. For example, if you are recording an absorption spectrum in the visible light, with the visible light, then your wavelength will change from 400 nanometer to 800 nanometer, and correspondingly the frequencies will also change, okay. So omega is a varying function, okay. So this will get affected because omega Fi is fixed, but omega could vary. So this ratio will vary. Apart from that, this sine function will vary because as delta omega varies, sine also will varies. Okay. But you see sine function can only go from 0 to 1. Okay. So, the sine square function also goes only from 0 to 1. Okay. In fact, sine function goes from -1 to +1, but sine square function can only go from 0 to 1. So, this function is basically modulating between 0 and 1. And now if I plot, okay, delta omega, this is 0, okay, that means omega Fi is equal to omega, this is equal to delta omega is equal to 0, and then you can think of some units 1, 2, -1, -2, -3, and then 1, 2, 3, etc. Okay. And if I plot this function here, that is nothing but sine square del omega t by 2 whole square divided by del omega by 2 okay, rather there is no t, I will just plot without the t, okay. Then this function will look something like this. Okay. Oh, this is kind of an exaggerated view, actually these will be even lower. Okay. So, this will hit the roof, this will go much more, and this will. So, which means your absorption, okay, will also happen away from the resonance, but so this is the resonance, okay. Delta omega is equal to 0 is also called resonance condition. Okay. It can also happen away from the resonance, okay. However, you will see that this will be very, very low. So, essentially away from the resonance we will still not be able to see transitions, okay. The major transition will happen, or the maximum probability of transition will only happen at the resonance, that is nothing but the omega Fi is equal to omega, and this is also called Bohr condition. Okay. So, essentially your Pf of t equals to E naught square by 4 h bar square omega Fi by omega whole square sine square del omega t by 2 divided by del omega by 2 whole square f this gives you probability of transition or absorption from initial state I to a final state F. Something like that. Okay. Now, one interesting fact is that this has got width. Like that. Okay. It has got a width, and this width has some important consequence. You know, we will go to the line widths and then we will discuss this. And the line width comes from this function. okay, and this function will tell us selection rules. Okay, so for a, and this will tell you effectively tell you intensity. So essentially there are three factors that determine the probability of a transition from a ground state or initial state I to a final state. One is the transition moment integral, that will tell you whether this action will be allowed or not. If allowed, what its value. Second thing is your modulating function, which will tell you how the line widths will come about, and third one will be intensity, that will depend on the how much light you are shining. Okay. So we'll stop at this point of time and continue in the next lecture. Thank you.